Okay, sounds good. Hopefully the audio is coming through well enough. Send me a chat if it's not, or send Xander one. It's a little bit strange giving a seminar and not being able to see people and interact with them. So bear with me. I'll try to get through this as quickly as possible so we can discuss any questions you might have. Okay, so what I'm going to talk to you about today is sort of a big picture look, mostly a big picture look at forests and cycle in the U.S., what we could do if we wanted to get them to store more carbon, what they're doing now and why they got that way. A little bit of history. I'm going to talk a little bit about some issues that are specific to the Southwest. Well, actually the West in particular, but the impact of the mountain pine beetle on carbon, and also talk about a little bit more about fuels treatments and carbon. So I want to say hi to a couple of folks that I know who are on there from this nice list that I'm seeing. Bill Grau, I haven't seen Bill Grau in ages, but Bill used to work for me about 15 years ago, and then Jim Allen, I just saw him in April. So hello, folks. All right. So what we did, the group of people on the previous slide, we got together for a few days and tried to come to consensus on issues about forest and carbon. So we synthesized the science, but we also, when we came to a conclusion, we also said this is, this is where we think we are. Which was an interesting and difficult thing for me, but I think definitely worthwhile doing. So we have two products out of this. One is on the web. You can get it from my website or the Ecological Society of America's website. It's an Issues in Ecology. We put a lot of work into making this understandable to folks who may not have the background in carbon cycling. We try to explain why forests are different than other things, and go through the options. We have a second paper that's in review. We just sent in a revision, so I'm pretty hopeful it'll be accepted here in the next week or two. It's going to be in ecological applications with all the citations and everything in there. So, I mean, it's essentially very similar, but we go into a lot more detail into the whys and wherefores in the ecological applications paper. So we were looking at two questions. First one is, what human actions influence forest carbon sinks, and can we enhance them? And then what are the trade-offs, the uncertainties, risks, and potential co-benefits? And the more we got into this, the more I realized that, almost everything we do, if we want to do it in a way that has an impact on our U.S. carbon budget, there's going to be trade-offs. And so if you don't remember anything else from this, hopefully you'll remember some of these trade-offs. There are very few free lunches in this game.
Yeah.
Okay, so here's where we are. This is a report that came out in 2007, a slide from that report. Mm-hmm. It shows North America, but, if you move everything down by about 80%, that's about what the U.S. is. Or no, by about 20%. Okay, yeah. So, I mean, the U.S.'s fossil fuel emissions are like 1,580 or 1,600. Somebody needs to put their microphone on mute. So I'm hearing something in the background. Okay, so there's a big disparity between estimates. The Forest Service and the EPA had a paper that came out about the same time this one did, and you know, their estimates were substantially lower than the estimates in the soccer report. And I looked into this some, and the difference, and this is big and it's important, but the difference is that the soccer folks included some really uncertain estimate for an increase in soil carbon and below ground carbon in their report, in their estimate, and the Forest Service EPA did not. You know, so that's a big number, but that's where the difference is. Okay, so let's give you an idea here about how big 10% is. Okay, so probably the most conservative estimate is that forests are offsetting about 10% of our fossil fuel emissions. So that's huge. It's just mind-bogglingly big, which I guess our fossil fuel emissions are even more mind-bogglingly big. But to get another 10%, we'd have to convert every U.S. auto into something that got hybrid gas mileage, you know, like 45 miles to the gallon, to get another 10%. Every auto in the U.S. Or we'd have to take a third of our current agricultural land and convert that to forests. So I just want you to think about those two things. Just think about how big that is and how much work that would be, and you know, how likely, I suppose, it would be that we would be able to do that. I see a chat on there. If folks are interested in the ecological applications paper, you can go to my website, which is on the first slide, and you can download a preprint, so it's on there. Well, it's instructive to think about, how did we get here? Why are the forests a carbon sink? Well, mostly they're a carbon sink because we're recovering from a long period where they were a huge carbon source. You know, if you can see this slide here, which is some slide of old logging taken by a guy in Washington named Kinsey, who went around and took all these logging photographs right around the time of that the peak in the red line. We were a nation that ran on wood. We deforested an enormous amount of land to plant crops. For agriculture, we used wood for just about everything, including most of the energy and that we got. And so right around, you know, in the early part of the 1900s, it peaked. And that peak emission is about 40%, I guess, of our fossil fuel emissions today. So our fossil fuel emissions are about 1,600 in these units. And then it started to decline as we started to use fossil fuels, and some of the marginal, less economic agricultural lands were abandoned to agriculture and went back to forests. So you can see in the next slide here, basically this whole hillside was cleared for probably pasture. It was in New England, you know, and this is all forests that have regrown. And so the taking carbon out of the atmosphere for the last maybe 40 years or so is because the regrowth and the filling in has been recovering carbon. Well, a good question is, will this sink continue? I mean, forests are providing this big ecosystem service right now, although, you know, for the U.S. as a whole, forests have put more, or we have put more forest carbon in the atmosphere than forests are currently taken out. And if you add up the numbers, we've recovered only about 40% of the carbon that was in forest basically before settlement. But if you look at it and think, well, how much more can we do? Almost all the agricultural land east of the Mississippi used to be forest. And so from a economic and food security standpoint, it's unlikely that we're going to put forests back there. Two other factors which we don't have a great handle on from a larger perspective. I mean, we know from plot studies what they do on plots, but how things work on the landscape we don't really know. We're getting increased end deposition and increased carbon dioxide. They're likely to increase the sink, at least where there's moisture available, and probably more for young forests than for older forests. But then we're seeing signs of increased disturbance, like bark beetle outbreaks and larger and more frequent fires, and perhaps larger ice storms in the east that are tending to remove carbon and tend to reduce the sink. Okay, so one of the things that I want to impress upon you, and most of you guys probably already know this, but is that forests are really different from all the other ways of thinking about carbon. So if you take a barrel of oil out of a well and you burn it, it basically goes in one direction. There's no cycle to it. I mean, some of that will eventually come back, but as far as the process of taking the fossil fuel out of the ground and using it for energy and having it end up in the air, it's pretty much a one-way street. Well, when you think about forests and carbon, it gets more complicated because forest carbon has a cycle. You basically go through, this is a lodgepole forest complex that I worked on up in Yellowstone. But, you go through regeneration, young, old forest, and then you get something beetle or fire, and then it goes back. Over the course of this, the net carbon gained or lost is zero. It's zero. You're not, as long as you recover the carbon that you lose in the fire and the subsequent decomposition, this is a carbon neutral cycle. Now, it takes place over 200 or 300 years, and so the timing may be important to us, but the total amount is not. So ecosystems, here's a plot of this from some modeling that we did based on data we took in Yellowstone. Xander, I'm hearing music. Is that?
Yeah, someone got us on our hold music. I'm afraid I couldn't mute everybody else, so everybody's got to be careful of their mute button. So far, we've done well, so I'm hoping we can fix this issue.
Okay. Well, it's not too bad.
The Melusina Overture by Mendelssohn, a work that the composer felt was really one of his best. Claudio Abbado led the London Symphony Orchestra and Julia Bacher. We'll hear the smaller version.
The person will identify they've got the radio on, and we can that. Otherwise, Mike, I could have you call in on the line, and then I can call other lines.
The Opus 3 collection. We're going to hear the Concerto Grosso.
Let's try that.
Sorry, I can't hear you.
Filled with wonderful instrumentation. You're going to be hearing a lot of.
Mike, can you check your email? I just sent you a code. Dial in on.
Okay, so I'll hang up and dial back in?
Yeah, with that other code, and then I can mute.
Okay. I'll do that.
Okay, so hopefully everybody can still hear me, and Mike should join us back with the music muted. Sorry about that. It's always a bit of a challenge to get all the technology right. So hopefully any minute here we'll hear Mike talking back in. Fingers crossed here. Uh-oh, I'm not sure this is working.
Dander.
Are you there, Mike? Oh. Is that you, Mike?
Yeah.
Did you dial back in with that other code I sent you, the 890 code?
Okay, I got it. Thanks.
Nothing's ever easy. Thanks for sticking this out, everybody. Maybe we'll...
Hello?
Ah, great. So now we have Mike and no music.
Good.
Take it away, Mike.
Okay. Okay, so this slide shows carbon. It's sort of a schematic. We put a model together based on data that we collected from Yellowstone. But basically, the fire itself doesn't take that much of the carbon out of an ecosystem. You know, what's in the foliage and what's in the forest floor or duff, some of the twigs, a little bit of the dead wood goes away, you know, usually about 10 or 15%. And then what our data shows is that in Yellowstone anyway, pools are still changing after 70 to 80 years, but the carbon is stabilized then. So the recovery, one of the surprises that we found from this research was that the recovery of carbon was relatively quick relative to the fire interval. So the big thing with fire or disturbance is whether you get regeneration or not. That's the biggest impact on the carbon cycle. If you get regeneration, you're going to, you may get a little bit more or less back than what you had before, but that's pretty small potatoes compared to one of these stand replacing fires in an ecosystem that's not adapted to stand replacing fires. So basically, if you look at this example here, in 100 years after a fire where you have a conversion from forest to meadow, you basically lost about half the carbon in the ecosystem. So this is something that's real critical and probably hasn't been recognized as much by folks working in this area as maybe it could be. Something else about forest carbon is that the larger the landscape is, the more stable the carbon is. You can imagine you've got patches going through these boom and bust cycles depending on disturbance or harvest or whatever, but as you get larger and larger numbers, as long as they're not in phase, it's very hard to have something move the carbon around. So the bottom line is that disturbance doesn't cause carbon loss or doesn't cause permanent carbon loss unless the forest doesn't regenerate. And when you're thinking about forest carbon, it's much better to evaluate it over large scales of space and time. Otherwise, you're looking at the bumps, which may or may not be important. Timing is important for economics, the time value of anything. You know, in this example from Yellowstone, okay, so it's going to recover all the carbon. We've got really good regeneration in almost all of the forests up there. But from 1988 to 2020, we estimate it will be a source of carbon, and it won't recover all the carbon for about 100 years. And so if we lose a lot of carbon over the next 100 years, when we're really trying to get a handle on the carbon in the atmosphere, the timing won't be good. So we need to take that into consideration. Even if we're going to recover everything, if we lose it for 100 years and then gain it back, the next 100 years is the most critical time for trying to keep carbon out of the atmosphere. So I want to take a little aside here because I worked up, we happen to have a whole series of studies where we have data on carbon in all the places that carbon can be in forests. And before mountain pine beetle outbreak, and we're going back and remeasuring them kind of as we speak here to look at how the mountain pine beetle and also the spruce beetle has changed things and rearranged it. So initially, when the beetles go through in the 3 or 4 or 5 years that it takes them to get most of the trees that they're going to get, the carbon stock doesn't change, but it gets rearranged. Okay, so I have, what you're looking at is 3 bars here, and so you have, this is the pre-treatment, or I mean pre-beetle outbreak, not pre-treatment, and then this is a post where we have mixed. So this is lodgepole mixed with spruce and fir, so maybe 30% of the trees are lodgepole, and so the outbreak has less of an impact. And then this would be a pure stand where 90% of the basal area or something has been killed. So you can take a look at that. Most of it's going from live trees to dead trees, and then there's a little bit of foliage going away. But basically you got a lot less live standing trees, and you got a lot more dead standing trees when the beetle comes through. That's not something that's a big surprise to anybody. So if you look at how these pools are going to be changing, before the beetle outbreak, the forests were a small carbon sink. And then after, in a mixed stand, they're close to neutral. They're a little bit of a source, but there's enough live trees there to keep them, to keep productivity up as a whole, and more or less offset some of the decomposition. But when you kill, 90% of the basal area, you've basically converted it to a sink for a while, and the sink is mostly coming, at least initially, from the decomposition of the coarse roots, the live roots, or the dead roots under the soil. So, okay, but let's look at it in perspective here. I just did some, this is real back of the envelope calculations, but so the big black bar here, that's our fossil fuel emissions, just calculated based on reported fossil fuel emissions divided by the number of people in the U.S., multiplied by the number of people in Colorado. So here's our carbon emissions. I mean, we were storing a little bit of carbon before the outbreak, and now we're losing a little bit of carbon relative to the, but they're both pretty small relative to the amount that we're emitting in fossil fuels. Based on our studies in Yellowstone, we looked at a replicated chronosequence. We had about 75 stands we went to and with various amounts of tree density. Tree density tends to converge as the stands get older, and so, you know, after that we broke, after about age 150, we broke them into whether they had beetles in there or not. And this would be for the 1980s outbreak. By all looks, it wasn't nearly as intense as the outbreak we're having in Colorado here right now. So basically, the left slide, this one here, these are just the rate of change, and here are the pools. And so the rate of change, basically, by the time you get to, you know, somewhere around 80 years, you've recovered just about all the carbon that you had lost in the fire. And because mountain pine beetle is not causing any immediate loss, like in combustion with a fire, and there's a lot of trees that weren't killed or advanced regeneration, it's likely that the recovery of carbon after the mountain pine beetle will be quicker than that after a fire. Okay, so let's get to the question, can forests do more to slow the rate of CO2 increase in the air? Okay, so there was a question from Don Falk about assume constant current climate. So basically that's what the landscape said. I mean, we went there and we looked at how much carbon was in each of these 75 stands based on age and density. We did look at future climate and how that would affect the recovery. And basically, over the next 100 years, it kind of depends on which climate model you use, but most of the scenarios predict for Yellowstone that we're going to get a little bit higher productivity because the increase in temperature doesn't cause enough water stress to offset the effects of a higher temperature. Now, that would probably not play out in the Southwest. Increase in temperature is probably going to be accompanied by decrease in precip, and if the forests grow more slowly, then it will take longer to recover. Although if they grow more slowly, they're going to decompose more slowly too. So it's a little bit tough to say, but they'll definitely recover a little bit slower. So before I get into the talking about ways that folks have thought about increasing forest carbon storage, I wanted to introduce two really, really important concepts. So the first concept is leakage. And leakage is changes outside the system caused by changing management inside. Okay, so one example and one way that folks have suggested storing more carbon in the woods is if you have active management, like say up in the Pacific Northwest or the Southeast U.S. where you've really got a lot of production forestry, if you can either reduce the amount of carbon coming out, so reduce the harvest intensity, or reduce or increase the harvest interval, increase the rotation, the net effect of that is going to be to have more carbon stored in the forest. All right, so that's good. Nobody would argue with that. Where the difficulty comes is with leakage. If so what that means is there going to be less product flow from those lands as well. So if there's less product flow, that means that either the price is going to get more expensive and we'll use something else, and we can talk about that, or it's just going to be bought in by someplace else where they're not concerned about keeping it in. And that's leakage. Basically, if we store carbon, we could, I'm pretty sure, we could take a lot of our fossil fuel emissions and offset them by growing trees on all our agricultural land. But then we'd have to get our food from someplace else where they'd probably have to cut down rainforest or whatever to find the land to plant the food for us. So the atmosphere really doesn't care who's doing it as long as it gets done. And from a standpoint of leakage, it's really difficult to say that our project here is not causing, something else, some other displacement activity someplace else. It's a really tricky thing in this business, and it's not easy to handle. The other concept is additionality. You can't probably read this, and you don't want to read it. All I want you to do is to understand that it's a complex and complicated thing. This is basically what carbon trading is about. So the idea is additionality is your project has to do something that's to get a carbon credit over and above what it would have done if just left alone. It kind of makes sense. We don't want to pay for something that would happen anyway. But when I look at this, I see something that's difficult, legalistic, and definitely not simple. And I'm not sure. Well, I'm pretty sure that I don't think we ought to go this way for forest carbon. I don't think we should. I'm going to suggest something else, but it's just you're relying on a whole bunch of uncertain things at timescales that may or may not be appropriate. So, for example, if you wanted to get carbon credits for changing your management, you'd have to do an inventory, run models for what it would be like without the management, run models for what it will be like after the management, take that difference and then convince somebody that the models are good enough that you ought to be getting a carbon credit for it. So if you look at the literature on forests and carbon, there's almost two separate sides, big dichotomy. One side says forests can really do a lot. The other side says we're going to have so much more disturbance that we're going to be lucky to keep the carbon we have. So I'd like you to remember this dichotomy when I go through these strategies because I don't know who's going to be correct. Just driving around right now, it's pretty obvious that there's a lot of disturbance out there. So tend to give that some credence. So the first strategy that we looked at was avoided deforestation, basically keeping forests in forests. And this is an important issue for the U.S., not just for the tropics. We're losing a lot of forests to development, some to conversion to ag use, some going back and forth. If we know anything at all for certain, we know that if you convert forest to something else, you lose carbon. So it's low risk. It's difficult to credit because it doesn't meet this additionality thing. It's already there. The forests are already there. It's got a lot of co-benefits. Keeping forests as forests does have some potential for leakage because you may just displace an activity someplace else. All the folks that are just deforesting the tropical forests are mostly not doing it because they hate forests. They're doing it because they want to eat or they want to sell timber to make money. So it's if you manage to retain the forest, you're going to have to find something to make up for the activity that they were getting out of the forest. So afforestation is another one. Reforestation, afforestation. Usually, there's some time limit in talked about. They're words that reforestation often means regeneration after harvest to a forester, but not to some of the folks in the forested carbon world. But if you think about it, did the area have forests before? If it did, you've got pretty low uncertainty, and you're probably not going to have too much trouble maintaining your forest because the climate's appropriate for it. If you didn't have forests there before, then there may be some issues. I know in South America, where they're afforesting on a lot of grasslands, they've got some salinization problems. They've got some water problems. If in our country, we'd probably to afforest in some areas, we'd probably have to supply water and nutrients. But evaluating whether or not you're getting carbon off of afforestation is really, really easy. You can basically see you're going to get more carbon. So the risks are low, but generally forests use more water than whatever it is that they'll replace. So if water is important, establishing forests is probably going to lower the amount of runoff. So the next one, and I talked about this a little bit, is to decrease outputs, whether increase the rotation or decreasing removals. You have to have active forest management to do this. In Colorado, this is not an option because we don't have a rotation interval or removals by and large, and so can't do anything with this. You're increasing diversity. You may have an increased risk of disturbance loss. You may have lower economic return, and you also may have some leakage as people go elsewhere to get products. Another place where if you have active forest management that you can do it is to increase inputs, increase growth rates by rapid reforestation, regeneration, fertilization, silviculture, species selection. You can read these things about the risks, but it does have a fair bit of carbon value with not too many trade-offs if you're already doing production forestry. So there's two things that have been talked about, in terms of wood products and biofuels. I don't know if any of you folks are familiar with substitution, but basically that's the idea that if wood gets used for construction as opposed to steel or concrete, the amount of fossil fuel that went into doing that, and the consideration that wood's a renewable resource means that it's going to require somewhere between, steel and concrete are going to have about twice or 4 times the carbon footprint of using wood. So for substitution, again, it's a little bit difficult to show additionality, but most of the building in the U.S. for housing is already out of wood. There's some, instead of using gypsum, you could use wood boards for that, but that's pretty minor. So basically, if we wanted to increase wood product use, we'd have to increase non-residential buildings. And there was a report put out by the EPA in 2005 that said that we could get 10% of our energy from biofuels. And I looked at that number and then compared it to what RPA, the Resource Planning Act, estimated as our annual net forest growth, and lo and behold, they were the same. So in order to offset 10% of our, to use 10% of our to use biomass as 10% of our fuels would require using all our current annual net production. That would also mean intensive management over very large areas, and it would require pretty large economic subsidies. So there's been a fair bit of literature in the last few years about fuels treatments as a potential carbon savings tool. So fuels treatments is thinning to reduce ground fire risk. It's got a low potential and a high risk because so far there are no evidence of that you're actually going to be saving carbon if you look at a landscape scale. So the way I tell people about this is, you're basically taking half, the biomass carbon off the landscape. Usually it just goes to, it just decomposes. And you're betting that against, the risk of actually getting a fire. Well, if you could just treat the areas that you knew were going to burn, you'd definitely have a carbon benefit because you're more likely to have live trees after a fire if you've gone through fuels treatments. The problem is that if you want to, you really want to protect your landscape, you got to do more. You got to do most of the area, and so on a landscape scale basis, you're taking out maybe half the carbon in the biomass, and you have to weigh that against how frequent fires are and how large they are to get a benefit. So one of the things that I have noticed when I've talked about this is that people assume that then, I think that fuels treatments are not good or something. And I'm just talking from a carbon standpoint. I'm a big fan of fuels treatment, so don't get me wrong here. I'm just saying, using carbon as as something to sell these is probably not going to work out. At least, based on the work that has been done on a landscape scale. Basically, you have to have a fire to get the carbon benefit, and so if global warming changes our climate, and increases fire frequency, well, the carbon benefit will increase. We'll get more carbon benefit if the biomass is used for energy. So the combined benefits for looking at all these potential things really depend on where you start. If you start from bare ground where somebody, has had the forest gone for a long time or never had it there, and you add up all these different ways, and this is basically using everything you possibly can use out of a forest. Then you can accumulate a lot of carbon benefits. However, if you start with a large amount of biomass and old growth, and then you clear cut it, basically, you don't get your benefits back even after 3 rotations, even assuming you're doing everything possible for it. So it really depends on where you start. So if you look at, I basically talked about things in the order of uncertainty and risk. This slide is just to remind you that, if you start out with something simple like avoided deforestation, it's pretty simple. It doesn't have much risk. The other options, you get risk or uncertainty increasing, and perhaps trade-offs increasing as well. So this is just a slide on the largest sources of uncertainty. So for our current estimates, we aren't really good at estimating carbon in soil and dead wood. We measure land use change, but we don't have a really good handle on that, and also we don't have a good handle on disturbance area. For the future, I think the pace of disturbance and especially regeneration and recovery is going to be the biggest unknown. And then whether how and when our sink's going to saturate, and then the idea of what we do to encourage or discourage this policy. So I want to leave you with a couple of final thoughts. The first one is, instead of trying to think about this really complicated, legalistic lawyers and accountants running through the woods, modelers, working with additionality and in carbon credits, why don't we think about just subsidizing the behavior that we want? And I think the Conservation Reserve Program is it's a pretty good example of that. Basically direct payments, for maintaining the land in a certain condition. It's a lot simpler. It may not be providing additional benefits always, but simplicity has a lot of value. I think when I think about the low-hanging fruit in any of this, making sure we get regeneration after large disturbances is key to maintaining this forest carbon cycle. And I think we need to do that. I know in the big fires we've had in Colorado, there's large central areas where ponderosa pine seed's just not going to get to for a long, long time. And increasing the rate and the pace and whether it actually happens at all of regeneration is something that we can do. Again, it doesn't fit into the carbon credit framework very well, unless you convince somebody that it really wouldn't have happened. But from the perspective of the atmosphere, it's really, really important. And finally, we have to remember that carbon is only one ecosystem service of forests. There's lots of things, and carbon, you know, is one of them, but we shouldn't be, I don't think, managing for carbon. Okay, so my 3 take-home messages here are that forests have a cycle, and they recover what's lost in disturbance if they regenerate. They currently have a large sink, but it may not last. And we should focus on retaining forests as the simple and lowest risk thing that we can do. Thank you very much, and there's a whole bunch of questions that came in that I was trying to ignore while I was trying to get through my talk. But I'm happy to stay on as long as anybody wants to stay on and talk about this. So.
Thanks so much, Mike. That was a great overview. I'm actually sitting in the middle of a thunderstorm, so I'm going to get off the phone here soon. But I'm going to open up the line here so everyone can ask questions in. But maybe, Mike, you want to start by, I saw that Don and Andy both had questions about the fuels treatment and carbon. So maybe we'll start with those, and then I'll open up the line for everybody else.
Okay. So I'm going to take, let's see, I'm working up from the bottom here from Don's question. Ecosystems don't have the capacity to absorb all the CO2 that is being emitted. Absolutely. I think we tend to want to do anything but to get away from our fossil fuel lifestyle. And I'm as guilty as anybody. But, you know, I mean, even at best, if we just put every, you know, if we did everything that forests could possibly do and didn't worry about where our food was coming from, you know, at best we could offset 20% of our emissions. Okay, so Andy wrote, over what time scale does the idea, if you only treat areas you know are going to burn, apply to? I'm not sure I understand what you're getting at. Andy, could you expand on that?
Yeah, can you hear me?
Yeah.
Okay. Yeah, what I was just, and I realized the whole point of that section was really to look at which are the most feasible things and with the lowest risk, and that fuel treatments really fall on the bottom of that. But I was just curious, you basically, you said, you know, it would make a difference if you treated only areas that you knew were going to burn. And in some systems, we pretty much know that everything's going to burn at some point. So it seems relative, yeah, so it seems relative to how fast it's regenerating what you've taken out in the sense of increasing your fire hazard and your chance of crown fire versus how frequent the fire is in that system.
Yeah. Yeah, I think the key is, you know, if you don't treat it, what's the probability of you getting, you know, a fire of X size or something? You know, what's that return interval? And then how much carbon would you lose in that versus what's the size and the probability if you do treat it? I've not seen anybody do a study like that, but I think we need to. Because, I mean, you have to look at it, like say if you treated your whole forest landscape, you know, you'd have much, much less biomass on there. Okay, and you say, well, how much biomass do we lose every year if we don't treat it? And then, you know, do the math on that. I think there's 2 studies, one by Mark Harmon's group and one by Elizabeth Reinhardt, that did this on a landscape scale, and both of them found that there wasn't any carbon savings. But, you know, I think that's what you have to do. I mean, it's relatively straightforward to go in and say, with a treatment, we've, you know, if you really change fire behavior, you're going to get more live trees when the fire goes through. I mean, that's pretty obvious, and we know that. And So, I just, my gut feeling says that we're probably not going to get a carbon benefit from this. That doesn't mean we shouldn't do it, but I think we need some more study too.
Yeah, well, and it seems like you would really only get a carbon benefit in really frequent fire regimes, where the chances of the fires across a landscape scale would be greater than you getting a return of all that biomass you removed in the same time frame.
Right.
It doesn't seem to make
tricky.
sense in long-term systems, longer fire regime systems.
Yep. Well, I think we need to look at it a little bit more. But I don't think it's going to be a big thing, from carbon. But I do think, in the just because you have to take so much carbon out, to get it to the point where they're relatively fireproof. It doesn't mean we shouldn't do it. I think we should do it. So Don had a question about, let's see, overstated given that there are models. Well, I don't know that those models have ever been tested, Don, but there are models. And then mastication, basically the stuff that's masticated is going to decompose relatively quickly, so it's it's lost to the ecosystem. Did that answer your question?
Yeah. I don't know if you can hear me, but just another area for some more work. What happens to that carbon under these treatments, the masticating treatments, which are becoming the dominant mode in a lot of areas?
Well, we're actually looking at that. So we have some decomposition rates, I think.
Okay, good.
Okay, Xander piped in, says using fields treatments to avoid catastrophic fires might prevent, something about, if you get a catastrophic fire, you're not going to get regeneration, and so if you don't, you might have regeneration come in for a future carbon. That's a good point, too. Yep, definitely. Other questions?
I'll ask one, Mike. This is Jim Allen. Can you hear me?
Hi, Jim.
Hi. I'm just curious, if within the context just of the U.S., and if you had a big chunk of resources and a lot of flexibility, where would you put your money in terms of geography and in terms of action primarily from a carbon perspective? In other words, would you try more intensive plantations in the southeast? Would you try limiting fire in the west? Where do you think you can get the biggest bang for the buck in the kind of short term, like say 10, 20 years?
That's a tough question, Jim. That's good. I like that. Wow. I think probably, the most bang for the buck probably comes from, is probably going to come from intensive silviculture. And it also depends on how much it would cost to retain forests, I think. Because retaining forests is, means you're not going to lose it in the future. So from the fire standpoint, like I said, I think it's going to come out from a carbon standpoint. There's from a lot of other standpoints I think we ought to be doing these restoration and fields treatments. But from a carbon standpoint, we're going to end up probably with being at best a little carbon positive. And so I think that's it. I think the idea of increasing rotations and whatnot is just going to be prone to leakage. That's going to be a problem.
So intensive silviculture silviculture might fit with CRP too. I'm not quite sure, but maybe.
Yeah, well, I think the issue with intensive silviculture is going to be what we do with that, because it's going to be unlikely that that the industry would make increased investments and let it sit there for a longer time.
Yeah.
Well, they're probably going to, if they do increase the investments, they're going to want to have shorter rotations. So it's going to be the amount of product that's coming out as opposed to probably leaving more in the woods. Great question, now. I'll think about that some